Very good morning to everyone. So I'm Gobi. So I'm going to talk about my research and experience with Mathematica. Right. So first was Peter, then was Farid, then finally was Desmond just now. All three of them somewhat distributing Mathematica, but I'm not distributing Mathematica. So I'm very much just a user, and I'm just going to share with you my experience with Mathematica. So now I'm working with the University Malaysia Terengganu. I did my degree, master's and PhD at USM. So when I was doing my degree, I learned Mathematica. During that period was version 3. Yeah, version 3. And I did my master's and PhD with Mathematica as well, in which I did in geometric modeling. Yeah. So my supervisor, Professor Jamaluddin, he did his PhD at University of Birmingham, and he used Mathematica as well. He did his PhD under the supervision of Professor Alan Ball, the guy who created a CAD system for British Airways. Yeah. So they design planes, design automobile. You need to use CAD system. So what we do is that we create algorithms. We try to formulate equations in such a way that we can create curves and surfaces. So with that, first I did like 30 slides. Then I try to increase to 40. Since I'm given time 30 minutes, so I'll just make it quick. In any way, if you want me to explain further, then please just ask me, then I'll do it. Yeah. So my title today is Empowering Industrial Design by Research-Led Teaching with Wolfram Mathematica. So basically, my talk will be threefold. The first one is on industrial design. The second would be research-led teaching, and finally Wolfram Mathematica. So basically, these are the three things that I'm going to talk about. So this is a table of content. As I said, first I'll talk about research-led teaching, then the essence of industrial design. Finally, I'll share my experience with Mathematica. So first of all, what is university? Yeah, what is a university? So this is it's written in Bahasa Malaysia. So what it says that pelajaran universiti atau college universiti artinya pelajaran yang diadakan oleh universiti atau college universiti pada peringkat persediaan pra-ijazah, lepas ijazah atau lepas kedoktoran, termasuklah penyelidikan, pembangunan pelajaran dan pengkomisionan. So university is not just on teaching, but we do research. That is what differentiates it between primary and secondary schools, right? So when it comes to university, we not just teach, but we do research. So if you look back at Germany and also Switzerland, they have this kind of kindergarten. It's called wall kindergarten. Yeah, it's in English, it's just a forest kindergarten. So they go to kindergarten in the forest. So they got to walk like 1 kilometer, go in the forest, then from there they will sit down and do activities. That's what they're doing at this moment. Yeah. So they are given real nice, and also they are exposed to fires, and they learn how to do things, even at kindergarten level. So these are the tools they use. So basically, you see forest, knife, and fire. What they learn is that, in fact, they did a PhD. A guy did a PhD research in what is the outcome of forest kindergarten. Is that their level of cognitive skills, social behavior, creativity, and physical ability are higher as compared to the normal kindergarten. Yeah. So basically, here what we do is that we show National Geography. They get to see documentary in such a way that they learn about forest. But now the pattern is very much different, where you are exposed to the real tools. Yeah, the real tools are here, other forest, knife, and etc. So back in university now. So we used to think that great researchers are not great teachers. Is it true or not? So how true it is? So we are researchers, great researchers, so-called, like they are very much into research. They don't have time for teaching, and then when they teach, they don't teach well. Is that true? So someone said true. So this is how you look like, right? So anyway, good teachers know their subject and good at delivering. We all agree with it, right? So they need to know the subject matter in such a way that they can deliver well. In fact, teachers are very good at diluting the subject. Yeah, they're very good at diluting subject in such a way that they can talk to standard 1, they can talk to Form 5, they can dilute in such a way that such that the audience understand what they're talking about. And good researchers know their material in depth and disseminate their findings. So if you find something, some result, if you don't know how to convey, again, you won't be a good researcher. So which means is that good researchers should be able to teach in a good way, right? So in fact, I argue that good researchers are good teachers, right? So what is research-led teaching? This is not by my definition, but by Troller, Wolfram, and at 2008. Yeah, research-led teaching reflects and makes use of teachers' disciplinary research to benefit students' learning outcomes. So basically what it means is that if you are good at a particular field of study, you are the one supposed to teach the subject. If you are not subject matter expert, then you would not be able to convey the knowledge in a proper way, right? So the research has to fit the teaching. So we have to package, for example, I teach geometric modeling. I have to teach geometric modeling in such a way that I embed what are the things, the outcome of my research findings. So that is research-led teaching. There are two stages in research-led teaching. The first one is so-called partial research-led teaching, where it's known as research-informed teaching. Yeah. So research-informed teaching basically lets students know what your recent findings. You let them know your outcome. Yeah. That's one level. But then the most important thing that you share is that your insights, your experience of deriving new knowledge, finding new formula, their insights, how you did that. That is the most important thing. That will spark fire for the students. Yeah. So basically, this would happen in social science related courses. And then the second one, so-called full-fledged research-led teaching, is you get your students involved with your research projects. So in such a way that, you have your research project, you have to break into small pieces in such a way that, of course, you got to dilute enough in such a way that your students would be able to participate and also author papers with you. So the traditional way would be lecturers provide list of readings, facilities, and advanced knowledge. But then the new way would be provide your research insight to the students. Yeah, and also build engagement with the students, get them involved to do research with you. So basically I have covered what is research-led teaching so far, and then how we are going to do it with Mathematica. So before we go into that, let me explain a little bit on level of understanding, level of learning. I'm sure you all know this Bloom taxonomy. It's a very old taxonomy. Yeah, where the lowest level of learning students learn is remembering. Yeah, you give a knowledge, they remember, they recall. Then in exam they recall and they write. And then the second level will be understanding. To understand, you need to explain. You got to write an essay and etc. And then you got to explain, analyze, evaluate, and then create. Create is the highest level of masters and PhD, where you create new algorithms, create new formula and etc. Right? So with Mathematica, in the geometric modeling courses, what we do is that we do exploration. I give equations in such a way that they get to explore Mathematica, how the curve is going to look like, how the surface is going to look like. They're going to execute those curves and equations as well. And then finally they're going to evaluate. Evaluate simply means that they're going to differentiate between maybe a curve type A to type B. Yeah, and see what are the advantages and disadvantages. Okay, so now I go to my second part of my talk. The second part will involve basically on curves and surfaces. Yeah. So we design curves and surfaces. Of course, an example of a curve is a polynomial curve, right? But normally, for design purpose in CAD systems, we use curves, parametric equations. Yeah, parametric equations. So, example of application: car design, electrical appliances, furnitures, jewelries, and then railway tracks, highways, roller coaster, even robot trajectory design, how a robot is supposed to move in a path, right? So these are curves, high quality curves, right? You cannot use simply any kind of curves to design this this type of application for this type of application. So those days, we go back a little bit, few centuries ago, they used to design with darks. This is something like a iron, made out of iron, it's with a weight. Then this is an elastic strip where you just pull and push with those darks, and then you get curves, beautiful curves. So from there you draw the curves. Yeah. Of course, it gets harder if you draw a huge blueprint, right? So you got to go up and on all that, you got to trace a curve. But then what they did is that, of course, we have competition power at this moment, so we design with CAD systems. It's pretty much the same actually. So instead of darks, now we use control points. These are control points. Yeah, these are control points. We just pull and push the control points such a way that we get different kind of curves and surfaces, right? So when I teach geometric modeling, what I do is that first of all we reproduce. Well, we pre-produce those equations. They get to know the equations. Let them know what the equations are, the polynomials, the type, and etc. Then after that, they were going to explore with Mathematica, right? And the best part about Mathematica is that they have these famous curves in them, yeah, built in. Yeah, so the famous curves are basically Bezier curves and also B-splines. Yeah, Bezier curves. You talk about Bezier curves are the curves used to design fonts. Yeah, those fonts in PDF, you see, very beautiful, right? So those curves are actually created based Bezier, either Bezier quadratic or Bezier cubic. Right, so who created Bezier curves? These two fellas are created Bezier curves. The first guy here doesn't look so happy, but this guy here, the name of this guy is Bezier, yeah, Pierre Bezier, and this guy is D. Casteljau, but he created the Bezier curve first, and he was working for Citroën. After a few years, this guy created Bezier curve at Renault, yeah, both very much in the automobile industry. But then it is known as Bezier curve because in Citroën they kept it secret. Yeah, and then Bezier is the one who made those curve famous. Right. Let me show you some example. So as you've seen just now by shown by Desmond as a Desmond on CDF file, it is very much easy to show that how the curve behaves, right? This is a Bezier cubic, right? In fact, I did a small file. Of course, you can just go to help file. You can see the whole thing. Yeah. Example. Okay, this is just a help file of Mathematica. Yep. So, in order to understand about a particular curve, how the polynomial behaves, you got to simulate and see how it behaves, etc. And then, of course, how to evaluate them. So, polynomial basically you want to evaluate faster. Use Horner's method to evaluate faster. But then there's another way of formulating the whole thing. You can use a D. Casteljau algorithm, where it is even faster. Anyway, by looking at just a help file, you'll be able to understand about Bezier curves better. And then, of course, these are control points, right? Very much pretty available with Mathematica. We can just call locator plane. It's called locator plane, where you can just call and then start creating your own curves and see how it behaves. You can also create your own fonts, yeah, with Bezier curves. As you know, as I mentioned, Bezier curves are used to design fonts in PDF files. It should be somewhere here. Anyway, due to time constraint, if you want to know further, I'll explain. Okay, so let me continue. So then we have B-splines. Of course, Bezier curve. The problem with Bezier curve is that as the degree increases, as the control points increases, of course you want to use control points. It increases, the polynomial increases as well. So when it comes to B-spline, it's very much different. You can use degree 2 with 100 control points. it is possible with B-splines. So B-spline was created by this guy here, Schoenberg, who was working for data fitting in finance, actual science. Yeah, but then eventually it's very hard. It's very hard to extract one particular polynomial, one particular B-spline. In fact, normally I give this as an exam to derive a Bezier B-spline in geometric modeling course. It will take about half an hour for you to derive one equation, one curve. About half an hour to drive just one curve. If you have actually practiced, otherwise it's going to take 1 hour, right? But you can do it Mathematica. At the same time, you can accelerate. Or of course, when it comes to CAD system, you do not use polynomial. You use a shorter way called D-Bohr algorithm. Yeah, D-Bohr algorithm by this guy called Carl D-Bohr, and he's still working at University of Wisconsin. So you can do things fast with Mathematica. At the same time, you get to understand the behavior of the curve and then derive from that, move forward from there. So I'll just keep on the B-spline. And this is a question that I asked for my PhD project. So what makes an industrial product beautiful? Yeah, this is back in 2006. The answer is curvature. Yeah, curvature for distance. In order to measure distance, you can use a ruler. In order to measure how much a curve is bending, it's called curvature. Yeah. So basically, curvature involves second derivative of a given curve. Yeah. Okay, as I drag, as you can see, as I drag, there's a circle, right? There's a circle moving along the curve. There's a red arrow and also green arrow. So the green arrow is a normal, red arrow is a tangent. Yeah, and then circle is actually an oscillating radius of curvature, oscillating circle, which the circle is actually the value, the radius of the circle is actually 1 over curvature value. Yeah, it's either going to be positive or negative based on the travel, how you travel from one point to the other. As you can see, there's a nice circle will sit on top of a particular point on a curve, tangent on the circle being tangent on the curve, right? So this is how you visualize the curvature. Yeah. So of course the curvature for a straight line is 0 because it's not bending, right? So the curvature for a circle itself is a constant. Yeah. So for a curve for you to design a particular object, industrial object, the curve supposed to have a curvature, smooth curvature, right? If you have a smooth curvature, which means you can manufacture the product. Yeah. So in order to do that, you have to look at the curvature itself, right? So if you design a particular curve, a particular shape with a Bezier or B-spline, once you design the curve with Bezier or B-spline, you need to inspect the curvature. Yeah, you need to inspect the curvature in such a way that the curvature is either monotonic increase, monotonic decrease. So I'll show an example. Okay, this is a piece of Bezier cubic, yeah, piece of Bezier cubic. As you can see, this side here is a curvature. The curvature is very much beautiful, yeah. It's just monotone increase. So if you use such kind of curve for design your object, your curve you will get a beautiful product once you manufacture. For example, this one here. So it goes up and then goes below. So there's a break in between. This is curvature extrema, they call it. And then, for example, here, these are the type of curves that you can't use for designing purposes. There's going to be some sort of like a bend somewhere in between here. Yeah. And then, for example, here. So this curve here, it has got an inflection point. Yeah, the curvature changes sign in between from From negative, it changes sign somewhere in middle. This is called inflection point, and then it changes at positive. So somewhere here it changes sign. So these are the curves that we don't want to use. We want to avoid all those inflection points for designing purposes. So how do we create curves in such a way that they are inflection point free or curvature extrema free? So that is the question that I asked for my PhD. Yeah. So Bezier curves and B-splines are very much for organic shapes. Yeah, organic shapes. Yeah, where you can the formulation is such a way that it is very flexible. You can design as you like. But when it comes to industrial product, highway design, we don't want such kind of flexibility, but we want to control over the curvature. So from curvature involves second derivative. So you integrate this, you get turning angle. Then you integrate turning angle, you get curve, right? So how you for example, just now I showed Bezier curve. I integrate the first, differentiate first time. I get its turning angle, or called as tangent, and then I differentiate again. I would be able to get curvature, right? So there's a nice theorem says that if you can create curvature first, let's say I represent curvature as a straight line, then I integrate it, I'll get turning angle. I integrate again, I can get a curve. So this process is called as curve synthesis. So we well define the curvature, then after that we create curve. So doing with Mathematica is very much straightforward. Yeah, you can just use 2 times integration of curvature, you'll get the curve. Yeah, either you can do it numerically and integrate. A simple command called and integrate, or you just use integrate directly if you want to get analytical solution. Okay, let me show an example. Two times integration. You see, so this is very much a straight line. Yeah, the equation is that this is the equation. Yeah, straight line. Yeah. So it's very much direct, right? By just a simple command as much as this. Yeah, this one is like, okay, we equate the curvature as sine s. So you get all kind of curves, right? As we introduce a variable inside this equation. So 2 times integration with the numerical approach. Yeah. So examples, many examples. These are the type of functions that I just simply create and show students. So now that we can create curves, of course I can create my own curves, call it as Gobi curve, right? But then it has got to have some certain level of quality. How do we define those qualities and say this is an aesthetic curve? So let's look at how Mercedes-Benz create their car, right? The car that at this moment in the road you can see is designed based on three natural products. Yeah, natural products. First is stingray. The second is the petal of orchids, the flower orchid. The third one is diatom, right? So from these 3 shape, they try to come up with a new Mercedes-Benz model. So this is somewhat so-called very much artistic model. From artistic model, they just further expand further. Then they get this sort of model. This is still again artistic. This is a Mercedes-Benz that you see at this moment on the road. Yeah. So the idea is basically from nature, right? From nature, from there they extract those curves. Then they got it. So back in 1999, a Japanese, Harada and his team, what they did is that they're going to scan all the curves nature, and then they scan all the curves used for car design. Then from there they found a graph called logarithmic curvature graph, where this is a rho. Rho represents radius of curvature. The circle, remember the circle that I showed? The radius of the circle. is the radius of curvature. So if you draw this graph, logarithmic curvature graph for a curve, if that curve in the form of linear, then that curve is called log aesthetic curve, right? That curve is called log aesthetic curve. So what we did is that from here, it is just a linear equation, right? It's just a linear equation. This is y equals to mx plus c. So y equals to m is alpha here, x is this plus c. So you get an equation. From that equation, we extract the curvature. From that curvature, we created curves. So this curve is now, of course, this curve is created by this Professor Miura. He's my collaborator, right? And then what we did is that we, in fact, furthered. Now it is available to use in a CAD system called Rhinoceros. We have already embedded and created a library for it, right? And for my PhD, what I did, one of my objectives is that I extended that curve. Yeah, it's called generalized log aesthetic curve. So I found that a generalized Cornu spiral, another curve used for highway design, it somewhat has certain properties that is very much pretty much the same as log aesthetic curves. So I tried to combine together. When I had jet lag due to when I was attending a conference in Czech Republic in 2008. So we actually used Mathematica, just quickly discuss and then how to combine further and make the curve to have a better two variables, more degree of freedom, and then it was very fast. That's why we created a curve called generalized log aesthetic curve, yeah, with Mathematica. And then when we tried to do, of course, I showed you numerically, right? Numerically, you can just do it very fast, right? Numerical, for example, Ranch-Kutta method, you can just do it very fast in the two times integration. So when you do it analytically, when you do it analytically, I will get some answers as well. So what I did, I got some answers. I really truly ignored the answers. Yeah, it was in the form of incomplete gamma function. But then after 2 years, this guy published a work representing that curve in the form of incomplete gamma function. Yeah. So this is what we missed. Right? Even though Mathematica gave us answer in the form of incomplete gamma function, but then we thought we didn't want it. We just want to see the curve fast, right? But then this guy did it, represented in the form of incomplete gamma function, published in a journal. Well, of course, these are Q1 journals. Yeah. And then, of course, you can also do it for other type of curves where you can also get in the form of hypergeometric functions. So, in terms of symbolic computing, Mathematica is super good, just super good in such a way that it will even give you this condition when a particular equation is valid. Yeah, and this is the final part. Yeah, so you can use Mathematica, you can use 3D printers. Farid also showed. Yeah, and I can create magic. Yeah, when it comes to geometric modeling, in my point of view, yeah, we can create curves. Then you can also print it. Yeah, and this is an example. Yeah, this is an example of a curve from aesthetic curve. We just created a product. Yeah, we printed it out in a 3D printer. It took us about 8 hours or so. It's very much crude. Yeah, it's as you can see, it's still got layers. You can see very much crude, right? So students should be able to do this sort of things. Students should be able to access this sort of products, this sort of tools in such a way that they can not just read theorems and then just then do some exercises. No, they need to get involved with it, extend that particular knowledge. So the outcome, what I anticipate, is that novelty and potential to innovate. Yeah. Then value of university credential linked to value of research outcome. So when we do just this teaching, it's not, you're not going to go anywhere. End of the day, you can do the best teaching ever possible, but then they ask how many papers you publish, right? What is your H index, right? What sort of Q journals you publish, right? So in order to increase that, you have to get good tools. You get to get them involved at a very early stage, such a way that when for example, once they reach undergraduate level, they are ready to do research and expand that knowledge. Yeah. So with that, thank you very much.